Hello viewers, in today's session we are going to discuss another important problem from integration, and here we are going to evaluate this integral with the help of the concept of gamma function. So here we have to evaluate this integral that is from 0 to infinity, and the integrand is x raised to n e raised to minus k square x square, and here we have dx, and the restriction on n is greater than minus 1, right? So let us see how we can evaluate this integral using the concept of gamma function. So let us first define a gamma function, and then we'll see how we can find out the value of this integral using the concept of gamma function and the substitution method. So the gamma function is denoted by say gamma m, and the gamma function is defined by this improper integral that is 0 to infinity, and here we have x raised to m minus 1 and e raised to minus x dx. So gamma function, that is gamma of m, is defined by this integral, and this integral is also known as Euler's second integral, right? So let us call this integral as I, and here first we'll apply the method of substitution. So let us take t is equal to k square x square. So we'll make this substitution, that is t is equal to k square x square, so that x square is equal to t over k square, and x can be written as square root of t over k square, that is equal to square root of t over k, and we can also write it as t raised to half, and here we have k, right? And here we have x raised to n. So if we take the nth power of x, then we can write x raised to n as a t raised to half over k raised to n, that is t raised to n over 2, and here we have k raised to n, right? Okay, so now we have x is equal to t raised to half divided by k. So let us differentiate x with respect to t. So we have dx over dt is equal to 1 over k, and the derivative of t raised to half. So we have 1 over k. The derivative of t raised to half with respect to t is given by 1 over 2 times square root of t. So we can now write t raised to minus half, and here we have 2k, so that dx can now be written as t raised to minus half over 2k, and here we have dt, right? And here the limits of integration vary from 0 to infinity. So let us change the limits. So when x is equal to 0, the value of t can be obtained from this expression. So we have t is equal to k square times 0 square, that is equal to 0. And when x tends to infinity, then obviously t also tends to infinity, right? So now we can write this integral in terms of t. So we can now write here I is equal to 0 to infinity, and for x raised to n we can now use this expression. So we have t raised to n over 2 divided by k raised to n, and here we have e raised to minus t, because k square x square is t, and for dx we can now write from here minus half over 2k, and here we have dt. So now let us first simplify this expression. So now we can write here 0 to infinity, and here we have t raised to n over 2, and here we have t raised to minus half. So we can write t raised to n over 2 minus half, and then we have e raised to minus t dt, and in the denominator we have 2 times k raised to n plus 1. So here we have k raised to 1, so adding n and 1, so here we have n plus 1. So now we can take 1 over 2 times k raised to n plus 1 outside the integral, being a constant, and here we have t raised to n minus 1 over 2 and e raised to minus t and dt, right? So now we have this integral, and we have to now convert this integral into this form. Now here the variable is x, and here the variable is t, and it is not going to make any difference. And here the exponent is m minus 1, and here we have n minus 1 over 2, and here we have e raised to minus x, and here we have e raised to minus t. So now we can take m minus 1 as n minus 1 over 2, so that we can obtain the value of m in terms of n. So we have n minus 1 over 2 plus 1, taking minus 1 to the right hand side. So this is n minus 1 plus 2 over 2. So m is equal to n plus 1 over 2. So 2 minus 1 is 1. So now we can write our integral I in this form: 1 over 2 times k raised to n plus 1. Here we have 0 to infinity, and here we have t raised to n minus 1 over 2, and n minus 1 over 2 is m minus 1, and the value of m is n plus 1 over 2. So we can now write t raised to n minus 1 over 2 as m minus 1, and here we can now write n plus 1 over 2 and minus 1 and e raised to minus t and dt. So now this integral is of this form, where m is n plus 1 over 2. So now we can write 1 over 2 times k raised to n plus 1, and this integral is equal to gamma m, where m is n plus 1 over 2. So we have 1 over 2 times k raised to n plus 1 and gamma n plus 1 over 2. So the value of this integral I can now be written as 1 over 2 times k raised to n plus 1, and here we have gamma n plus 1 over 2. So this is the required value of this integral. So now the value of this integral is given by this expression, and we can use this expression to find out some particular values of this integral, right? So if we take, say, n is equal to 0 in this integral, then this integral reduces to 0 to infinity, and we have x raised to 0. So x raised to 0 is equal to 1. So we have simply e raised to minus k square x square dx, and now the value of this integral can be obtained by taking n is equal to 0 in this expression. So we have 1 over 2 times k raised to 0 plus 1, and here we have gamma 0 plus 1 over 2. So here we have 1 over 2k, because 0 plus 1 is 1, and here we have gamma half, and the value of gamma half is equal to square root of pi. So here we have 1 over 2k times square root of pi, right? So the value of this integral is given by square root of pi divided by 2k, and we have obtained the value of this integral by using this one, by taking n is equal to 0 in this integral. So now further, if we take the value of k as 1 in this integral, then we have 0 to infinity, and we have e raised to minus 1 square x square dx, and here we take k is equal to 1, so we have square root of pi over 2 times 1. So the value of the integral 0 to infinity e raised to minus x square dx is equal to square root of pi over 2, and this is a well-known integral.